Alright, so today, rather than digging into what Chris has been up to, which is producing more ads, we're going to look at some slop. A nice big healthy bowl of slop from faceache. Now, if you're on faceache, you've presumably noticed that there's an awful lot of slop on there. What you will notice is that there's an awful lot of people producing the same thing. Well, I say people producing the same AI produced slop, just slightly differently, and you might be wondering why. So we'll get into that in a second. So anyway, here we go. Here's an essential fasteners guide. Hey, great, straight out of faceache. Yes, hex nut. Yes, hex bolt. Yes, wood screw. Isn't somebody's been having a really good time? Flat washer. Not really a fastener. Yes, parallel key, I guess. That looks just a bit like a kind of a parallelepiped. Stud bolt. Well, yeah, okay. That's not a pop rivet. That's a rivet. That's a wedge anchor, probably. That's a nail. Yes, that's a threaded insert. Yes, that's a retaining ring, but it's not an internal one. That's an external circlip. And that is probably a clevis pin. Now, this is presumably pulled straight out of an AI. Give me a diagram of essential fasteners. It gives us no useful information as to what we might use them for, no useful information about where we might not want to use them, no useful information about what sort of load they're useful for. In fact, this is absolutely useless shite. Next, if we can, yes, probably have to select that. All right, here we go. I'm going to have to zoom in on this. This is in French. Fundamental workshop tools, but what you can see, fundamental workshop tools, precision. Fiabilité is reliability, precision, reliability, and performance. So these are the fundamental workshop tools to give you precision, reliability, and performance. And what we're looking at the top here, hang on, let me have a look. Let's see if we can scroll this, shall we? Up. In fact, what I'm probably going to do is go full screen, but hey. So, why precision gives us better machining. It gives us security and reliability. It gives us longer life of our work and optimal performance. Isn't that nice? Well done. Thank you very much, AI. Now, what have we got here? The fundamental workshop tools are an exterior micrometer, a vernier caliper, a lathe tool, a 3-jaw chuck. Okay, we'll get on to the 3-jaw chuck in a minute. So, what have we got here? So this is, again, straight out of an AI. What have we got? We've got an external micrometer. Let's look at the external micrometer, shall we? Now, the labelling is almost right. There is an anvil, which is a fixed surface reference surface. The arrows aren't pointing to the right place. The anvil is here. There is a movable spindle, which normally is aligned with the anvil. But hey, this is obviously a special micrometer. It does have a lock to lock the spindle. It does have a barrel, and it does have a drum. And the barrel is used for reading the major units, not necessarily millimeters, and the drum is used for reading the minor units, not necessarily hundredths. And it does have a click mechanism to give us a constant torque on constant load. And what's it used for? Well, it is used for measuring exterior dimensions with a great precision, or with a relatively good precision, the precision of the micrometer. So, that all looks pretty good. Those numbers look a bit peculiar. You can see those? Yes. Those numbers look a bit peculiar as well, but hey, it's come straight out of the AI. Now, we've got some useful formulas. Are these to do with micrometers, do you think? Oh, what have we got in the formulas? Well, we've got cutting speed, rotational speed, diameter of the workpiece, initial diameter of the workpiece, rotational speed again, and our advance. No, I don't think those are necessarily relevant to micrometers. Now, let's look at those formulas, shall we? Cutting speed is equal to the cutting speed multiplied by what? No, that's nonsense. Right, the rotational speed in revolutions per minute is 1,000 times the cutting speed times pi times the initial diameter. That might be right, I'm not sure, I can't work it out off the top of my head, but yeah, okay, but it's probably not equal to the cutting advance in millimeters per rotation, is it? Again, this is nonsense. And then, some key values. 1 turn of the drum is 0.5 millimeter on a micrometer, not on any of mine. And 1 graduation of the drum is 1/100th of a millimeter. It is on mine, but not necessarily on yours. Again, nonsense. Now then, let's look at the vernier caliper. This is actually a vernier caliper, very near as they're known. It does have interior jaws, exterior jaws. It does have a screw to block it in most cases. It does have a vernier, and it does have a graduated ruler. The graduated ruler is for the principal reading, and the vernier is for the fractional reading, but not necessarily in terms of millimeters. This one is in millimeters, it says, and it's a special caliper because it goes 0 millimeters, 2, 2, 3, 15, 6, 16, 13, 13, 18, 13, 14, 15, thing. Yes, well done, Mr. AI. And then we've got some peculiar stuff on the vernier as well. Now then, how do we read that vernier, do you think? Well, okay, let's look at the characteristics. Oh, it's got a depth gauge as well. There you go. So, characteristics. Yes, it's got the typical vernier caliper is 0 to 150. This does say it's an example. Precision, 0.02 millimeters. No, the precision of a vernier caliper is not 0.02 millimeters. That might be what you can read off the vernier. It does not mean that the tool is precise to that. The precision of a vernier caliper is normally around 0.05 millimeters. That's what the manufacturers will guarantee them to. What are they used for? Internal measurements, external measurements, depths, and shoulders. Shoulders, it doesn't show you how to measure a shoulder. The shoulder measurement is done using the back of this slide and the end here. But hey, how do we measure? Well, we take our principal measure from where the 0 shows up. This doesn't really explain it very well. And then we read from where we actually match one of the other things on here. We add the two together, and that gives us our measurement. Now, so this one apparently says 32 millimeters. So from 2 millimeters, 20 millimeters, 21, I would say that's a 21 millimeter reading. That's not 0.18, that's a 4. That would be 21.4 millimeters, not 32.18. Now these are special millimeters as well, because special centimeters. These are centimeters on the top. So 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2. 32 here. Yes, there are 12 divisions in a centimetre, and there's 5 divisions in a millimetre. Well done. That's really 5 divisions in 1/10 of a millimetre. That does not give us the precision that they think. Excellent. Let's look at a turning tool. It's got a screw to tighten it down somewhere. Yes, probably. It's got an insert. Yes, it's got a seat. Okay. What type of inserts are current? Well, there's the most common: TNMG, CNMG, DNMG, VNMG. These are N is not necessarily the most current, but there you go. So the T-type, C-type, D-type and V-type, yes, 60 degrees, 80 degrees, not 0 degrees, 55 degrees and 35 degrees. These are not the most current. And we've got example TNMG. What? Nonsense. So, what does that reference mean? T is the form, N is the clearance. N in this case is neutral, which means that it's got a 0 clearance. M is the tolerance. G is how it's fixed and what chip breaker it's got. Then we've got the size and thickness and what the diameter of the tip is. That is actually correct, although it doesn't explain anything, and it doesn't explain any of the other variants that you might have. So, principal functions, taking material off, yes. Finishing or roughing, yes. It's adapted for steels, stainless steels, cast iron, or various other materials. You might have different ones. High precision machining. So this is partially, mostly correct and utterly useless. Good. Here we go. The 3-jaw chuck. As we all know, a 3-jaw chuck has 4 jaws. It has a body, it has jaws, which are also in the body. It has conical guidance. It's got 4 conical guidances. And it has a key, which is also in the body of the chuck. It can rotate in either direction. Yes, it can. And it holds the piece axially. Does it? I suppose. Possibly. Maybe. Yes, well that's nonsense, isn't it? What types of chucks do we have? Well, there's the three-jaw auto-centering chuck, which has 4 jaws that are not necessarily aligned at 90 degrees, which gives a automatic centering. It's for cylindrical pieces and usual work. Okay, maybe. The 3-jaw chuck is mostly that. It doesn't look like that, but there we are. And then there's the 4-jaw independent chuck. Yes, you can adjust each jaw independently. It's for asymmetrical or square pieces and gives you a better centering precision. Perhaps. There are other types of chuck. Are they here? No, because this is nonsense and it gives us absolutely nothing. Oh, look, we've got some formulas again. It's the same formulas, but this time they're shown as formulas, cutting formulas, not useful formulas. So we've got cutting speed, which is different to the one above, but also dependent on cutting speed. Well, that's obviously nonsense. We've got N as the same as above. F, which is the feed, but this is feed per tooth. So that's for milling, and it explains absolutely nothing. How many cubic meters of chips per minute do you want to... no. This is nonsense. Absolute fucking nonsense. What's next? Let's look at the next page. Oh, this one's good. Now, we can zoom back out. This is from OAS Cycle Centre. Let's make it a bit bigger, shall we, so we can get the whole thing in. This is great. This is an infographic on motorcycle clutch assemblies. So we've got clutch spring bolts. Those do look like bolts. They're not going to go through the springs, but hey, we've got clutch springs. We've got a pressure plate. Yes, okay, we're good so far. We've got clutch plates, which are friction discs and steels. Yes, we do. We've got friction discs, where it's pointing at the steel plates, and we've got steel discs where it's pointing at a friction plate. Okay, we have clutch friction material, and a steel disc. So the friction material is both the steel disc and the friction material. Nice. Inner clutch hub, yes, we've got one of those. We've got a primary drive gear. Why we've got to pull out for that, I don't know. We can see it perfectly well from here. And apparently there's an internally operated clutch mechanism. Yes. There's a main shaft, which looks like a washer. There's a thrust washer clutch hub nut, which looks like this. There's a push rod, which looks a lot like a bearing, and the push rod assembly and the push rod bearing are attached to the crankshaft. That's going to be fun at 15,000 RPM. The clutch lifter is on the crankshaft. Yes. We've got a nonsense power flow diagram. We've got another pull out here. This is apparently a copyright-free original design, but at least I'm not going to get copyright struck. And it's certainly original. Oh yes, that was fun. What have we got next? Oh, planetary gearbox. Now this one's great. So this is an epicyclic gear set with a labelled anatomy. Let's have a look, shall we? Look at what we've got. We've got the gearbox housing. That looks a bit like a housing, kind of, sort of. We've got an input shaft. That looks like an input shaft with an oil seal on it. And we've got an output shaft with an oil seal on it. And then we have a planet gear and the same planet gear again. And another planet gear going all the way around the outside. That's nice. We've got a sun gear, which is the input. Quite how that connects to the input shaft, I don't know, given that it's at 90 degrees to it. There's a planet pin, which looks a lot like a planet gear to me. And there's a planet gear bearing, which is a needle roller. And there we are, that's there. And then that's another one just there. There's a housing flange and an oil filler plug at the bottom. That's always handy. There's a snap ring, which looks a lot like a roller bearing. And then there's a planet carrier bearing, which is also the same thing. The ring gear is apparently this, which is good because that ring gear there is the wrong way round, as well as being sideways. Good Lord, isn't that wonderful? I hope we all now understand how a planetary gearbox works. There's an oil drain plug as well, but we can't see it. It's invisible. Now this is absolute fucking Facebook nonsense. It's great, isn't it? It's really fucking wonderful. One of the people on a forum I was talking to, who's pro AI, I kind of pointed him at some of this and said, look, go and ask one of your AIs to give you a chart of bearing fittings for 6,000, 6,200 and 6,300 bearings from 0 to 60 millimeters input size, interior diameter. Different types of bearings and what it can be done. What it can be done. What am I talking about? Talking absolute nonsense. I've been looking at too much AI slop. And what they're used for. So this is the best result that we got. Absolutely the best result, remember. Now to zoom in a bit more, if we can get that there, and we can zoom in. Again, this is in French because my mate is French, and it's a French language forum. So this gives us some drawings. So 6,000 standard series, 6,200, which is a light series, 6,300 is a super light series. This is kind of correct. The diameters and stuff are pointing in the right place on these diagrams. Remember, this is the good one. Some of the others were absolutely fucking hilarious. Codes for the different various types. So 2Z, ZZ, 2RS. How much interior play there is. So normal play, C3, C4. Other variants might be NR for groove and circlip, N which is grooved, TN9 which is polyamide, TVH. There's other ones, and it doesn't give us all of them, but it gives us some useful variants. That's pretty good. It gives us drawings of some of the useful variants as well, which is kind of, yeah, that's all right. I can live with that. Although N and NR, if you can't see the groove, the drawing is useless. Now, if we look at here, the 6000 series, an example, 6204. Oh, but 6204 is not part of the 6000 series. 20 by 47 by 14 is not the size of a 60,000 series, 60,004. That's the size of a 6204. So it is the correct size for a 6204. Gives us 6204 again here in the 62,000 series. Again, correct sizes. And it gives us the 6304, correct sizes. And then we've got some principal sizes, so from 10 through to 60. This is all good. The 60,000 series, all the sizes are wrong. They are the sizes for a 62,000 series. 6200 series. These are the 6200 ones, which have got the sizes for the 6000 series. And these are the 6300 series, and they are correct. So, what we can glean from this is that AI can almost give us something useful, but you have to check. I had to check all of these sizes, and this is basically just a Google search. The others were absolutely fucking hilarious. I mean, really, big D shown everywhere. You know, we've got an R here, which is showing a radius somewhere. R is never referenced in any of these. Oh, it is referenced here actually. That is correct. I think those R dimensions are correct. They probably are, but these are standardized. Values can change slightly between fabricants. No, they can't, or they shouldn't. A 6302 is a 6302. It's made to fit a hole for a 6302. It's made to fit a bearing seat on a shaft for a 6302. They do not vary. That's what standards are about. Anyway, I said I was going to get into what's going on faceache. I got talking to a couple of the people producing some of these faceache diagrams. They are AIs. They are engagement farming and trying to get better. In fact, that's really quite funny. So, what's a really good thing to do is to correct them, and correct them badly. Correct them wrong. That's a really, really good thing to do. So, for example, on a set of bearing diagrams, if you were to correct them and tell them that the 6000 series, they've got their dimensions all wrong, that would be great. AIs are shite. They should be removed. But that's just my opinion. Anything you get from an AI, you have to check, so you might as well just do your research yourself. Anyway, I'm off. That's our helping of Slop. Bye.